this is the parallel session, the standard model parallel session, just in case you wonder where you'll ended up. So we'll have 6 talks in total about a mixture of LHC and Hera physics, or deep inelastic scattering collisions in a broader sense. So it's almost, I think, time to start. I'll try to keep the timing so people can easily move from one session. Who wants to move from one session to another can do that easily. So the first talk is by Daniel about jet measurement in CMS. So thanks in advance, Daniel, and I'll let you speak.
Yes, thank you very much. So let's then get right into it. I will be talking to you about a series of recent jet measurements in CMS. So just to start with a little brief overview of why this is really very interesting to look at. So of course, first of all, your jet data is very sensitive to a number of things that are very interesting. So like fundamental parameters of the standard model, you have the strong coupling, which directly enters these processes. And so you can use this type of measurement to constrain that sector of the standard model. And you can use it to constrain Darton distribution functions, which of course enter the initial state of any process you want to look at a Hadron Collider. So you benefit a lot from looking at this jet data to constrain those as well. And well, jet measurements tend to, or jets tend to be really very abundant at Hadron Colliders. So because of that, you get kind of a high statistical precision with these measurements. And then if you combine these measurements, so for example, you have jet cross sections together with fixed order theory predictions, which have also become quite accurate. So these are known to next leading order in perturbative QCD right now. And you put them together in a fit, you can hopefully increase the knowledge on PDFs, which are just shown here in this sketch. So that's one reason they're interesting. Another reason is that you can use them to really go even beyond the QCD sector. So if you have reduction in association with jets of some other objects like top quarks or the Higgs boson, you can use the jet precision to really constrain those sectors and even look beyond the standard model to some extensions like effective field theories. So I'll be touching mostly on the direct measurement topic in this talk. And maybe going into a little bit beyond QCD as well. So getting right into it, one measurement I'd like to talk about is very recently published. This is inclusive jet production at 13 TeV. And this is a double differential measurement of the inclusive jet cross-section as a function of PT and rapidity. And it's done with 2 sizes of jets. So it's done with the 0.4 cone size and a 0.7. And this is very interesting to look at sort of radius dependent effects. Then you have shown here on the right, you see that the phase space for this measurement is quite large. So it's going from a PT of the jets to just below 100 GeV to up to 3 TeV. So you can probe all of this, and the rapidity goes up to 2.0 here. Now, one thing that was done for the measurement is, of course, a comparison to the perturbative predictions. So here you see the comparison of data to predictions at next leading order, plus a resummation correction and next leading logarithmic, and next to next leading order calculation. And you see that the points go very close, much closer to unity when you go to next leading order. So it's really a nice improvement here in terms of the description of data by the theory. And another thing that you can see is, however, if you look at the top plot at NLO, there is also a comparison to the predictions for different PDF sets. And you see that particularly at the high PT region, they tend not to agree with each other that well. So hopefully by inputting this data into the PDF determination, you can get the PDFs to kind of agree on what the cross-section is in this high PT region. So the way this is done for this measurement includes an analysis, which is a fit of the PDF parameters together with the strong coupling constant done at next to next leading order. So this is done in a traditional approach where the PDF is parameterized with a Hera PDF-like parameterization, which you can see here. And it's giving some quite satisfactory results. So if you look at the PDF at the bottom left here, you see that compared to a fit that only includes the HERA data, which is not that sensitive to the gluon PDF, and then you add the CMS 13 TV jets, you get a significant reduction of the uncertainty, particularly in the high X region here. So this is very nice to see. And on the strong coupling constant front, you get a value that is quite similar to what has been obtained in previous CMS analyses, and also is compatible with the world average. Now, in particular, the value of 0.117 is sort of kind of average or expected, but you see that the scale uncertainty, which was previously rather large, is now only at 8 in the final digit here. So this is an improvement that is due to the next to next leading order. The overall fit quality is quite good. So we have 1.1 chi-square per degree of freedom overall for the combined fit. So altogether, very nice, satisfactory look at standard model QCD in next to next leading order. What was also done with these data is that a combined fit with PDFs, the strong coupling and the top pole mass. And this also includes the TT bar data, because this is the one that is sensitive to the top quark mass. So by fitting these results simultaneously, the idea is to actually constrain the PDFs and the strong coupling using the inclusive jet data, and then try to use the TT bar data to get a better fit of the top pole mass. So you see that these results are also in nice agreement with what is kind of expected for the top mass, and with previous results. There's compatibility with previous results obtained for CMS using only the TT bar data, and the strong coupling constant value doesn't change that much compared to the PDF plus alpha is only fit. Now, another thing that you can do is, as I said, to look beyond the standard model. So in this case, an addition to the standard model was considered where the 4-core contact interaction as an effective field theory was taken into account. So here, the Lagrangian is expanded by a series of dimension 6 coefficients, dimension 6 operators, and you have the coefficients of these operators, which are the Wilson coefficients. So actually, you can fit these. And in particular, there's only one coefficient you can fit. So it's the C1 coefficient, because the value of the others is given by the coupling structure. So you have one free parameter that you can fit, and there's also the energy scale here. Now you can see for a particular energy scale, the results from this data. So you have values that are very close to 0, which is the standard model expectation. It's slightly negative, but there's not really a significant excess to indicate that there are contact interactions beyond this, beyond the standard model. So we've also investigated a large energy range in the energy scale, so going from 5 to 50 TeV, and we can turn this into an exclusion limit as well, which is roughly of 24 TeV for a particular contact interaction model. The PDF itself doesn't change very much, so this is an indication that we are able to actually constrain the PDFs and even look beyond the standard model without affecting the result of this fit here too much. Now, just to briefly show you a complementary measurement of inclusive jet production, this is done now at a lower center of mass energy using only the smaller cone-sized jets. And without going into too much detail here, this is a very nice playground to look at the scale dependence and the PDF dependence of this type of data and these predictions. So you have at next to leading order here a comparison between two central scale choices, and you can see that one of them works slightly better than the other. So this is the HT parton scale, which works at next to leading order much better, but the scale uncertainty, which is this red band, is still relatively large. Now, if we go to next to leading order, the band gets reduced, so the scale uncertainty is now smaller, and you can start looking at meaningful comparisons of the different PDF sets. So they also give you slightly different results. And another thing is that you can use this for determinations of the strong coupling. In this case, the best fit, or rather, it's not really a fit, but it's going through the PDF sets for different alpha S values. And the observation is that the larger alpha S values work slightly better for describing data. Now, moving on to a different type of measurement, this is now multi-jet production. And the idea here was to do a measurement of the PT spectra for the 4 leading jets in the event. The reason why this is very interesting is because you start to rely more and more on parton showers to describe your high multiplicity. And There's also an interesting new approach for determining these predictions, which is the part unbranching approach coupled with transverse momentum dependent PDFs, and the comparison between these types of models and the more conventional part-on-Shire plus collinear PDF approach is explored. And you can see here the next leading order models, they have a lot of variation for the high PT when looking at the leading jet PT, whereas when you go to the next leading order models, they start to become more and more compatible. And we also see that the conventional and the TMD approaches also yield comparable results. In the same vein, there is also a measurement of the jet multiplicity, but this is just basically counting the number of jets in various phase space regions. And this is looking now in different regions of the angular separation of the jets. So you have the back-to-back configuration here at the right, which has a strong perturbative contribution. And then as you go to the smaller separations here, you start to see a larger and larger influence of the parton showering. So this is interesting to evaluate these, the performance of these models as well. And here, while at leading order, you can see relatively nice description. Next leading order, as you go to high multiplicities, you start to see that the models begin to fail describing the data. So here, there is some improvement that can be achieved as well. Now, the final aspect I want to present to you is this very interesting measurement of jet substructure, which I think is a very good input to sort of these types of studies. So jet substructure is a nice tool, in this case, particularly for distinguishing between the various types of jet flavors. So if you look here at, this is just one example of a substructure variable, which I'll get to in a moment. But if you just look at it, this is a comparison of a dijet and a Z plus jet sample. And the main difference between these types of samples is that they have various proportions of gluon-initiated jets and quark-initiated jets. So a distinction here would mean that you can distinguish with this variable very well between the two flavors. And indeed, you see that the peak and the mean value of the distribution is slightly shifted depending on which sample you look at. So this is actually a very nice premise. And a large number of measurements was performed here looking at very different things. So the substructure variables themselves are quite varied. So we're looking at generalized angularities here, which are just combinations over the jet constituents of momentum fractions and jet axis. Distances from the jet axis with various powers to control kind of the relative contribution of both things. And there are kind of a few traditional values for kappa and beta, which are the parameters of these angularities that you can choose. There's the Lazouche angularity, the width, the thrust, and some other variables that are interesting to look at with different properties. And then you can do all sorts of things. You can modify these calculations or these measurements to only take into account charge constituents. So this gives you an increased experimental precision by relying on the more precise resolution of charged particles due to the tracker. And you can use a soft drop approach to kind of call the low PT end of, or the low energy part of the jet. So finally, you can look at what this
Daniel,
result is.
you have about 2 minutes.
Okay, thank you. Yeah,
Good.
so this is my last slide. You can look at what jet substructure measurements actually result in. So this is comparing predictions to data of these jet substructure observables. So what you see here are the 5 variables that I mentioned before in the different colors. And each variable is measured for very different configurations. So here the 1 through 5 tells you basically a combination of a jet radius, a PT range. Sometimes you look at only the charged components, or you use groomed jets for it. So these are really very extensive measurements. And there's 2 things that you can see here in this comparison. So in the top row, this is a ratio of the substructure variable for gluon enriched and quark enriched ratios. So there is a significant difference from 1 here, which is at the bottom of the plot here in the first 4 panes. And you see that because of this significant difference, you get quite significant discriminatory power between these 2 types of samples just by looking at the individual substructure variables. So this is looking very promising. However, if you look at the simulation of a data ratio, you see that there are still quite some issues with describing the data. So the Monte Carlo models tend to overestimate the measurement in many of these configurations, and which can have a number of reasons. So there's a strong perturbative contribution here in some variables, and others like the multiplicity and the PTD squared have also a significant contribution from non-perturbative effects that need to be taken into account. So overall, we see that this is promising, but the models involved need to be a little bit more refined before this can be used in a really fully precise application of distinguishing quark flavors. So now I arrive already at the summary. So not to go into too much detail here, but I've shown you some recent results from CMS. The main ones were the inclusive jet cross-section measurements at 13 TeV and the complementary measurement at 5 TeV, and their comparison to the theory, which is now known to next leading order. And there have been very detailed analysis of the PDFs and the strong coupling constant, also looking into things like the top mass and the 4-quark contact interactions beyond the standard model. And there have been some other preliminary results involving the multi-jet observables, which is relevant for parton shower modeling and comparison of different models there, and an extensive investigation of jet substructure, which reveals that some Monte Carlo models are in need of improvement. Right, so with that, thank you very much for your attention. So if there are any questions, please go ahead.
Thanks, Daniel. So does anyone have any question? Okay, so I'll give you a bit of time to raise your hand and try to ask a question myself in the meantime. So I actually have maybe one or maybe two questions. So first, when you presented the impact on inclusive jet data to extract the PDFs, have you used, I think it was one of your maybe slide 4, around slide 4, something like that, maybe. Yeah, good. That includes both values of the jet radius or just one of the two?
Oh yeah, that's a good question. So this is just using the large radius jets, the 0.7 radius.
Okay.
And the reason for this choice is that in the past, these larger jet radii have seemed to be more robust in such studies when comparing directly to the fixed order theory. So that's what was taken. I'm not really sure if the 0.4 jets were in any way investigated, but the main result is definitely for the 0.7.
Yeah, I guess you have something similar on your probably on maybe the previous slide when you showed. Yeah, I think from what I remember, if you look at the NLO plus NLL calculation versus the NNLO, that one has probably a slightly more robust description of the two jet radii, more consistent. There's still an undershooting or overshooting depending on what relative to what you're talking about, but at least the NLL tends to slightly alleviate the tension between 0.4 and 0.7. So I was wondering whether that would have an impact in the fit. So yeah, okay. 0.7 I think is the standard one to use here.
It wasn't used in the fit, but I think I have a slide showing you the 0.4 results as well. So this is just a comparison to the theory. Okay. Sometimes it works better than the large radius, but here and in NLO you start to see some effects. So I can't really speak to more precise things here. Yeah.
Have you tried the NNLO plus jet radius for summation?
I don't think this has been tried, so it didn't enter the final result. Not aware if there were any internal studies on this, unfortunately.
Okay, thanks. Well, I see Francesco has his hands raised.
Morning.
So please go ahead.
Yeah.
Hi, Daniel. Thanks a lot for this very comprehensive talk on these new CMS results. I have a question about your slide 4. Can you go back, please?
Sure.
It's about the chi-square. As you probably know, also Atlas tried to fit the inclusive jet data, both at 8 and 13 TeV. And we have never achieved such a good chi-square as you do in this table here. So my question is, do you have you applied any decorrelation for the systematic uncertainty, or in particular, I don't know, something related to the jet systematic uncertainty, or, I mean, this is the quality of the fit straight on.
So the systematic uncertainties have, of course, different dependence depending on which phase space region you are in. And this is, I think it's very extensively divided into the different sources. So these are all things that do enter the fit. It's not a decorrelation per se, because this is really the standard way to look at, for example, jet energy scale uncertainties within CMS. So I don't think there's anything done that really differs from what was done previously, except that probably now the determination of these uncertainties has been looked into a bit more detail since a lot more time has passed. So this is essentially what comes out of the fit firsthand.
Okay, I mean, I can tell you that Atlas, to give to obtain such a good chi-square, I mean, for example, I mean, we fully decorrelated among the various rapidity bin the jet flavor response systematic. So I was wondering if you did something similar.
Right. So unfortunately, I don't know if any complicated correlation of this type of systematic has been taken into account. I think it's really very basically either 100% correlated sources or completely uncorrelated ones. So there's no study of how the correlation can impact this result. So this is probably each of the systematic sources for the jet energy scale is considered to be 100% correlated across all regions.
Correlated?
Yes.
Okay, thanks.
Although you have a split in things like ANTCAP sensitive regions and barrel sensitive regions, so there is indirectly a form of the correlation. The model is quite complex. Fortunately, I can't really go into too many details here since I don't have them. But yeah.
Okay, thanks. I will have a look at the paper. Thanks a lot.
Thank you. Yeah.
Okay, so good to have a discussion. Actually, that last question is a perfect transition to the next talk. So thanks again, Daniel, for this review of the CMS results. Yeah. And now we're going to be moving to Evelyn's talk, who's going to be speaking about actually PDF determination from jet measurements in Atlas. Again, that's a perfect transition. So Evelyn, can you share your slides?
Yes, I'm trying. I don't understand why it doesn't work. Just 1 second.
Good.
Okay, what is the problem here? Okay. Okay.
Good. Okay, so please go ahead.
Okay, so good morning and good afternoon, everyone. It's a pleasure for me to present today the latest result of the Atlas collaboration on proton-parton distribution function. So, as you know, PDF are key ingredient to provide theoretical prediction at the LHC. And I just remind you that PDF uncertainties are the dominant uncertainties for high precision measurements, such as the Wmax and the weak mixing angle. They are also important limiting factor for the X physics, and they have also an impact on searches. Indeed, the discovery of new physics rely on the precise knowledge of PDF. Currently, the frontier high energy physics cut colliders require percent-level accuracy for PDF in order to resolve potential effect of beyond standard model physics in high precision standard model measurement. And now LHC experiment may contribute to this effort. As you know, currently LHC measurements are used in global PDF fit, and they provide an important complementary information to dataset from DIS and fixed target experiment in a corner of phase space previously unexplored. But we can contribute further to these efforts. Indeed, PDF fit from LHC collaboration not only allow a first direct test of the sensitivity of PDF of our measurement, but they also represent a precious vademecum for global PDF fitting collaboration on how to use LHC data in the fit. And the Atlas experiment has always been in the forefront of this challenge. In the past, we published a PDF fit where we used the ERA data plus the Atlas inclusive WZ cross-section measurement at 7 TeV. And the fit provided the separation of quark flavor. Adding to this fit the boson plus jet cross-section measurement at 8 TeV, we were able to provide to probe higher X for this quark flavor separation, while adding the TT bar cross-section measurement in a fit with ERA data plus the inclusive WZ cross-section measurement at 7 TeV, we probed the gluon distribution at medium and high X. Today, I'm going to present the latest result of the Atlas PDF fit for the first time at a conference. It resulted in the Atlas PDF 21 set, where we further enhanced the sensitivity to PDF, including in the fit a much larger amount of Atlas data, and where we performed detailed tests that are relevant when the aim is a percent level accuracy. So, in addition to the WZ inclusive cross-section measurement at 7 TeV that have been already used in previous Atlas fit, now we are using also the available result at 8 TeV. And depending on the dataset, we used the differential cross-section measurement as a function of the lepton rapidity, the rapidity of the boson, or the polar angle of the lepton in the Collis-Stopper frame. For what concerns the boson plus jet data at 8 TeV, in the fit we used, as done in the past, the PT of the W boson and the rapidity of the jet in different bin of the jet PT for the Z plus jet dataset. We also used for the first time the inclusive photon result of the Atlas experiment, in particular the ratio of the cross-section measurement at 13 and 8 TeV as a function of the transverse energy of the photon in different bin of the photon rapidity. For what concerns the TT bar measurement, we used, as done in the past, the several distribution of the TeV result in the dilepton and the lepton plus jet channel, and we used for the first time the 13 TeV result of the lepton plus jet channel. Of course, we couldn't ignore our inclusive jet measurement. In the fit, we used the jet PT distribution in different bin of the jet rapidity at 8 TeV, and we performed a detailed cross-check with the 7 TeV and the 13 TeV dataset. So here I show the summary of all Atlas dataset used in the fit. We fit more than 600 Atlas data point. The backbones of the fit remain that ERA data that indeed provide good constraint in a quite large range of X, but we have to take in mind that we need Atlas data in order to provide the flavor separation in the C and the gluon PDF at high X. We fit the data with prediction that are NNLO in QCD plus electroweak correction at NLO. And this is the current state of art of modern PDF. And we used the X-fitter framework for the fit. So here I show the parametrization that we adopted for U and D valence quark, for light anti-quark, and for gluon. The normalization parameter AI and the slope parameter BI for the light anti-quark are assumed all independent to each other, and this strategy has only recently been adopted by some global PDF fitters. As done in the past, we assume that the S distribution is equal to anti-S. The AI parameter for valence quark and for gluon are set by the some rule. For what concern the D, E, and F parameter appearing here in the polynomial, they are added for each distribution until there is no further significant improvement in the chi-square, and this results in 21 free parameter in the fit. For the gluon, we added this negative term here, where the exponential here is set to an high value in order to avoid the negative contribution at high x. For what concerns the chi-square, the form is the standard one adopted in ERA and in Atlas PDF fit. I would like to stress that we considered the correlation of statistical and systematic uncertainties within and between Atlas dataset. And here in this table, I show the correlation scheme for systematic uncertainties between different datasets. The correlation of jet uncertainties, and in particular the jet energy scale correlation, play the dominant role. This is somehow expected since the jet energy scale are the major uncertainty for most of the measurement. But we also considered the correlation of smaller uncertainties like the lepton and the background uncertainty when relevant and when available. We performed a detailed study on the correlation, and here I show the impact on correlations as an example for the D-valence, the anti-D, and the gluon at a scale that is relevant for the LHC physics and focusing in the range of middle X, where W, Z, and X are produced. Here we compare the result of the nominal fit in red with a fit where the correlation between datasets are ignored. We see that the difference in PDF are not large, and PDF uncertainties are similar. The main impact is on the D sector, but correlation can be important when the aim is a % level accuracy on PDF. And let me now discuss the impact of the different datasets. Here we compare the result of the nominal fit in red with the result of a fit where we removed some dataset in blue. So, without the W plus the WZ inclusive data, the strange density that here is represented as the ratio of the strange to the light antiquark, as you see here, is very poorly determined. If we fix the attention on the nominal result, the red curve, we see that is confirmed the unsuppressed strangeness at low X already seen in previous Atlas fit. We see here that without the W plus jet data, there is very little information on the strange density at high X. This big change of the curve is due to the fact that the boson plus jet data resolve a double minimum in the rest of the data that marginally prefer the blue configuration. And this effect has been already studied in detail in the previous Atlas publication on PDF fit using the boson plus jet data. So when we add the TT bar data, we get a gluon distribution that is softer at high X, and the uncertainty in this region get reduced. As expected, the main impact on jet and gluon is on jet and direct photon is also on gluon in the IX range. In addition to the experimental uncertainty that I show in the previous slide and that are the dominant uncertainty to the fit, we also considered the parametrization uncertainty, adding extra parameter to the fit, and the modeling uncertainty, such as the variation of the minimum Q-square of the ERA data, the starting scale of the fit, and the masses of the heavy quark. If we look at the result, we see that the experimental uncertainties are better determined in the U sector than in the D sector. For what concern gluon PDF, it is well determined for central value of X, but we are still dominated by large uncertainty at low and high X. We also performed
So Evelyn, you have about 3 minutes left.
Okay. We have also performed a detailed study on the scale uncertainty. I remind you that we fit the data to NNLO QCD predictions. So scale uncertainty are in general smaller than experimental uncertainties. They are compatible with experimental uncertainty only in the inclusive WZ production case, and so in this case they have been included in the fit correlated between W and Z and between 7 and 8 eV. And here we show the impact of the scale treatment for the D-valence, the anti-D, and the gluon. In red, as usual, the nominal fit. In blue, the result of the fit where scale uncertainty are not accounted, and in green, the result of the fit where scale uncertainty are treated as uncorrelated. We see that overall the effect of the scale uncertainty is not large, but again, it can be important when the aim is a percent level accuracy. We also studied the impact of the scale uncertainty on other datasets, and as expected, it has been found negligible. We also performed a detailed study on the chi-square tolerance in previous atlas and ERA-fit, as in the plot I shown until now. The experimental uncertainties have been evaluated with a chi-square tolerance equal to 1, but now we have to consider that we are using more disparate atlas data. We know that some global PDF group use enhanced chi-square, other group use other method but obtain similar uncertainty. So we performed a study on appropriate tolerance applying the procedure of the MSHT group, and we adopted tolerance equal to 3. We see here that when we compare the atlas fit with this criterion with the other the global PDF fit, we get indeed a similar uncertainty with some difference that is anyway understood. Just as an example, the larger uncertainty of the atlas fit at IX for the U-bar distribution is due to the missing fixed target Drelian data in the atlas fit, or the larger uncertainty at IX of the gluon distribution is due to the missing jet Tevatron data. And let me finally present the result of the atlas fit with full uncertainty, again in red, compared with global PDF fit. We see that the atlas fit agree with the global PDF fit as well as they agree to each other. Moreover, the atlas data bring the PDF much closer to the global PDF than the ERA PDF 2.0 shown here and here in orange. And so this brings me to the conclusion. We fit all available atlas data sensitive to PDF that have information on correlated systematic uncertainty. We fit our data to NNLO QCD plus NLO electroweak prediction. I already discussed in detail the impact of the different datasets. An enhanced tolerance is used for a realistic PDF uncertainty estimation, and the atlas fit is in reasonable agreement with the modern PDF. I would like to stress again that the correlation between datasets have been included and the information is made public to global PDF fitters. We also considered the scale uncertainty when relevant, but the aspects are relatively small but important for future high precision measurement of the standard model parameter. And I would like to say again that this work represents a precious vademecum on the treatment of the atlas data for global PDF fitting collaboration. I've done. Thanks a lot for your attention.
Okay, thanks a lot, Evelyn, for this detailed talk on PDFs in Atlas. Does anyone have a question? We have actually a few minutes for questions. No, so I don't see any hand raised. Let me ask something then. So you investigated the effect of different data sets on the PDF extraction. I vaguely remember hearing in the past that there was some tension between the TT bar and inclusive jet sets, data sets, especially on the high X gluon. Is it something that you see as well, or or?
No, in the sense that, okay, going here. So what we see now that we add all the data set is, as I said in the talk, that the TT bar move basically the gluon distribution software. And this is due to the fact that somehow when we include the JET data, they move instead the gluon PDF harder. But they are anyway consistent. There is not, let's say, a significant discrepancy. It's just...
Okay, thanks. I see Daniel has questions. There's a question. Sorry, go ahead, Daniel.
Yes, hi. So first of all, thanks for the really nice talk, for the comprehensive look into the PDF. So you mentioned at the beginning that you are using the 8 TV data from the inclusive JET side and using the 7 and 13 TV as a cross-check. And I was wondering what this cross-check looks like. So are you just substituting then in the big fit the 8 TV inclusive jets with the 7 and the 13 and looking at the impact, or
Yes, so I have a backup slide on this. First of all, we used the ATV data in place of the 13 of the 7, because for ATV we had the available result at 0.6 in radius, and we have also the result at 0.4, so we used the difference of the two as modeling uncertainty. I didn't mention it in the talk because it's a small contribution with respect to other model uncertainties. Later, what we did basically is summarized in these two plots here. So we substituted, we ran basically the nominal fit, so ATV data are 0.7 with this is the comparison in blue with the result with the other radius 0.4, so this is the effect of the change. And later we run the 13 TV data that are available only at 0.4, and the result is the green line here, and the 7 TV at 0.6, the other result. And we see that within the total uncertainty of the fit, the difference are negligible, basically. We cannot use all together the JET data because we don't know the correlation of the uncertainties, basically. So this is the only way that we had to prove it.
Okay, thanks. Yeah, so really nice. It's just that just a small additional comment. So the other data set seems to really sometimes reach the edge of your uncertainty. So it definitely is worth to fit the data in some way together. But as you say, the correlations need to be worked out. So yeah.
Yes,
maybe this is a nice idea for.
Yes, exactly. Maybe in the near future.
Okay, but thanks very much. Yeah.
Okay, thanks for the questions, talks, and everything, and the answers, Evelyn. I don't see anyone else, so I suggest we move on to the next talk. So we're going to switch gear a little bit and now move to physics. And I guess the first speaker of the series is Henry, talking about one jettiness in the bright frame at high Q square. So Henry, hi.
Hello.
Can you share your screen?
Looks good.
Perfect. Thanks. So
all right. Great. So thanks for having me. I'm lucky to be following some nice talks. So disclaimer, it's 4 a.m. for me. I'm on the East Coast in the US. So if I'm not making sense, just ask me for clarification or send me an email. All right. So we're looking here at this kind of jet shape observable, the one jettiness in the bright frame at high Q squared. And at Hera, we're looking at neutral current, deep inelastic scattering, which is a clean collision system where we have direct access to the kinematic variables that we know and love, namely Q squared, Y, and Bjorkane X. So the bright frame, for some people involved in hadron colliders, is maybe slightly unfamiliar, but it's basically the frame where the incoming parton has its momentum more or less reversed. So it's sometimes called the brick wall frame, because one can imagine it as the parton coming in, hitting a brick wall, and coming out. And I use kind of a few things to describe this. So it's cleanly divided into two hemispheres, one of which is called kind of the beam or remnant or target hemisphere interchangeably. And this kind of over here on the left, this HB, is where kind of the remnant of the proton ends up, whereas this HC is kind of where the struck quark ends up. So you get a nice geometrical separation between the two processes. So what we're measuring is the one jettiness event shape, which is a infrared safe and theoretically clean observable because it's free from these kind of non-global logarithms that complicate things. And it's sensitive to alpha S and PDFs, and it can be calculated quite precisely in soft collinear effective theory and PQCD. So what this observable is it's the minimum dot product of every particle in the event with one of two vectors. And these two vectors are defined by basically the beam and then some jet axis, which is defined by the kinematics of the event. And there's kind of an equivalent definition that follows from momentum conservation, which is more or less just the sum of the longitudinal momentum in the bright frame with a normalization factor. And it's nice because only in this definition, only particles in the current hemisphere contribute, which is experimentally favorable. So we're using here the H1 experiment at Hera with a root S of 319 GeV. H1 is a hermetic detector with an H-symmetric design, had a drift chamber and silicon tracking, but kind of the centerpiece of the detector was the high resolution liquid argon calorimeter that did a great job measuring both EM and hadronic particles. And particles are reconstructed with kind of a particle flow algorithm, and the trigger is highly efficient for Y less than 0.7. So if we look here at some event displays, on the left here, we have basically a DAS1 jet event where you can see that, so this kind of spray of particles is the jet, this kind of gray line is the scattered electron, and you can see that you have a nicely collimated event. And in this case, you have a small tau1b because the dot product with the so-called QJ of these particles is low. On the other hand, when you have kind of a dijet event or a kind of spherical event, you have a large one jettiness by definition. So the nice thing about event shapes is that they're inclusive observables. And so one needs to look at the inclusive DAS observables. So in this analysis, we're looking at Q squared greater than 150 GeV squared, and inelasticity Y between 0.2 and 0.7. And we're analyzing the 351.7 inverse picobarns collected during the Hera 2 data taking period. The two kind of signal Monte Carlo generators we're looking at are RAP gap, which implements matrix element plus parton shower approach, and Django, which implements color dipole model. And despite the name RAP gap, both of these are kind of full DAS generators. It's not just photo production. So the backgrounds for this measurement are quite small. The dominant ones are kind of photo production and low Q squared neutral current DAS, kind of faking as a high Q squared DAS. And in this case, the DAS kinematics are reconstructed with the I sigma method, which has the nice feature that it's independent of the potentially damaging QED ISR, which is kind of a pain in the neck when you're trying to reconstruct the kinematic variables generally. So since this is kind of a fully inclusive observable, all events contribute some value to the tau spectrum. Well, that's interesting. That's supposed to be the equation. Anyway, so in these plots here, 0 degrees is kind of so each particle kind of also contributes some amount to the spectrum. So with 0 degrees defined as kind of the proton going direction and 180 degrees defined as the electron going direction, we can break out into the individual normalized contributions to the observable, you know, whether it's a track or a cluster and what energy. And we see that tracks in kind of the central detector region from 25 degrees to 135 degrees dominate the spectrum, with also a large contribution from clusters in the central detector, both of which are generally well measured. And then if you look at the energy of these individual particles, the majority are tracks and clusters with greater than 1 GeV, which are well measured in general by the detector. So kind of the fundamental quantity when we're looking at this tau q for the measurement is this PZ bright, because that's basically what we're summing over. And when we look at this, we see very good agreement between the H1 data and the detector simulation, which is these curves of Django and RapGap here, both for clusters and for tracks. So that's great. So here's kind of the first, when I'm first showing you the actual tau q spectrum. So this peak on the left here is more or less Born level like DIS 1-jet events. As you go to larger tau q, you get, so these events are kind of dijet events greater than 0.5. And then this large spike at 1 is dijet events where both jets end up in the beam hemisphere, because looking at this definition here, if you have no particles in the bright frame, your tau q is 1. And you can see from this plot here that the detector simulation does an okay job of describing the data, but you can clearly resolve the differences between these two models, especially in kind of the higher tau q region. So the way we kind of went about doing this measurement is kind of a bin by bin correction technique, where the cross section is kind of defined as the number of events in the data minus the number of events in the background divided by the luminosity multiplied by a bin width correction. This C unfold is a constant taken from comparison of particle level simulation and detector level simulation. And then the CQED is kind of a QED correction factor, which is taken by comparing radiative and non-radiative Monte Carlo. So the cross section that we're reporting here is basically the particle level. We're extrapolating the data to the non-radiative particle level. So looking at our plot over here, we see that the kind of peak region is not really especially well described by any of the models in this plot. RapGap and Django kind of underestimate the data, while Pythia plus Dyer tends to overestimate it. In the kind of larger tau region, RapGap and Django do a little bit better, but Pythia plus Dyer underestimates. So if we compare some different parton showers just within Pythia, you can see that the peak region is really quite sensitive to the specifics of which model you're using. So Pythia plus Dyer, Pythia plus Vincia, and standard default kind of Pythia 8.3 give quite different results. And really none of them really completely capture the data over the full spectrum. We also have comparisons of the process EP to 2 jets plus X from NNLO jet. And here non-perturbative corrections are just taken out of Pythia. And in general, they're large at low tau 1b, which is kind of expected. But the NNLO plus non-perturbative corrections really does quite a good job, kind of the best job at describing the tail region, which is kind of to be expected, so that's good. And you can see here kind of the difference between the red and the light blue is quite sizable at lower tau 1b. So the nice thing about doing things inclusively is you can break it out into a triple differential measurement in tau 1b, Q squared and Y, the inelasticity. So in these kind of patch plots, we have increasing Y, or we have increasing Y from left to right, and then we have increasing Q squared from bottom to top. So as you increase Q squared, you see that generally the peak tends to shift further to the left, as one kind of expects. You expect your jets to be more collimated. And you also see that the tail region kind of dies off at higher Q squared, which is also kind of to be expected. So that's great. As you increase Y, you can kind of see that this peak at tau equals 1 tends to increase in size a little bit. And that's kind of from just the kinematics favoring the case where both jets end up in the beam hemisphere in the bright frame.
So Henry, you have about a bit more than 2 minutes left.
Okay, great, thanks.
Thanks.
So here I have plotted the ratios to the data. The statistical uncertainties across these bins range from a few percent to a few tens of percent. The systematic uncertainties in most of the bins are around 5%. Django and RepGap generally do a good job describing the full phase space. And in general, Pythia and Dyer are a bit too large. To compare to some more models, I have here also Pythia with the default shower, Pythia plus Vincia, and Herwig. Herwig has some kind of strange behavior. It underestimates the DIS cross-section, and it also has kind of this bump. So this may be something with this version of Herwig that we're using. We're still kind of ironing that out. So to now compare triple differentially the NNLO prediction, you can see that at the lower Q squared, the non-perturbative corrections, which are basically the difference between this red line and this light blue line, are increasing, whereas at higher Q squared, they're more or less negligible. The NNLO with non-perturbative corrections kind of everywhere does the best job at describing the data, even better than Pythia, and quite significantly better in some places than the NNLO. So in summary, this has been the first measurement of the one jettiness event shape and neutral current DAS. We agree quite well with perturbative QCD predictions. Upcoming is a comparison with the N3LL prediction and an NNLO plus parton shower. And in general, this observable is kind of highly sensitive to model parameters. So it'll be very useful for tuning the Monte Carlos, especially since we have a US-based electron-ion collider coming soon. And we're looking to explore the sensitivity to alpha S and the PDFs in a little bit more detail. And a combined extraction of these two quantities should be possible. So in general, it's a promising measurement for the EIC and other future EP colliders. Thanks.
Thanks a lot, Henry, for this nice analysis. So does anyone have an immediate question? Okay, I'm getting used to this, so there's no questions. Let me ask something. So I was actually going to ask you 30 seconds before the end of your talk whether you had investigated recent predictions for this, since you motivated that at the beginning that there's ways to get high accuracy precisions calculations here. So you briefly mentioned you had the N-cube-NL in the pipeline.
Yeah. So that's I guess being done by Chris Lee and collaborators. Okay. And yeah, that's kind of a in progress calculation and in comparison with the data.
So I suspect you're going to have potential issues with non-perturbative corrections or big non-perturbative uncertainties in that region.
Yeah, I guess it's a matter of yeah, I guess it's a matter of how they choose to handle that. I don't know the details of the theory
Well,
calculation.
I guess
but-
you can go to high Q square, because I was looking at your one but last slide, where it seems indeed that non-perturbative corrections are much smaller at higher Q square. Yeah, that one.
Right.
Do you know if that extends down to smaller values of tau? Is what I wanted to ask.
Well, so in the fixed order, I would imagine, yeah, I would imagine that, I mean, it's because at low tau, you're really looking at the, one jet. It's a one jet event. So basically it's all kind of non-perturbative. I don't know. I would imagine that. So typically that's kind of captured in the NNLL predictions.
Okay.
They kind of do a better job describing that region than the fixed order.
Okay, I actually have another small question, which is there any other jet shape you'd like to measure, which would potentially be either going in the same direction as one jettiness or give complementary information?
Right. So we also kind of have some preliminary measurements in the pipeline of the kind of more standard event shapes, broadening, thrust, things like that.
Yes, sphericity and whatnot.
Right. So that's also something that we're looking into. And then we're also doing a measurement of groomed event shapes as well, which is something that's kind of new and interesting.
Yeah, that's one of the things I had in mind as well. So thanks for mentioning it. Yeah, I guess in particular in the peak region, that can seriously decrease your non-perturbative uncertainties and hence be more helpful for tuning Barton-Shuber Monte Carlos, for example.
Exactly.
Okay, well, thanks a lot. Is there anyone willing to ask something? Last chance. Okay, well, thanks a lot, Henry, for giving this talk in the middle of the night.
Thanks for having me.
I hope you managed to find some rest before or after. Okay, so still staying with Hera physics, we're moving to Zeus now. So Devon, I hope I'm pronouncing this
Devon.
right. Devon. Okay, good. Thanks for the fix. Okay, so Devon, so now it's okay. Devon, you're going to speak about azimuthal correlation in photo production on behalf of Zeus. So please feel free to share your screen and go ahead.
So you heard me and you see me, yeah?
I hear you. I see you perfectly. Next step is the slides. Thanks.
Okay. All right. Now you see the slides.
Good. Perfect. So still the middle of the night.
Yes, also for me. Okay. All right. So yeah, I'll be talking about azimuthal correlations in photo production and deep elastic scattering at Hera with the Zeus detector. So there are two motivating questions for this analysis. The first one is, how small can a colliding system be while still exhibiting the collective features typically associated with this so-called quark-gluon plasma that we observe in heavy ion collisions? And then the second part of the analysis is about multi-parton interactions. And it's we try to understand the relationship between MPI and this collective environment that's observed in heavy ion collisions and also in smaller hadronic collisions. So yeah, I'll be presenting recent measurements with the Zeus detector in both neutral current DIS and photo production. And we have a new publication on this subject. So we start with observations in heavy ion collisions, namely lead-lead at the LHC. So this on the left side, you see a what's called a ridge plot. It's a two-particle correlation. So delta eta is the separation pseudo-rapidity of the pair. Delta phi is that in azimuth. And you see this double ridge. So there's one ridge here with a jet peak in the middle, and then an away side ridge. So a near side ridge and an away side ridge. And this feature, long story short, is interpreted as a sign of fluid-like behavior, but a QCD fluid, not a QED fluid. And that's what's called the quark-gluon plasma. And okay, so that was observed roughly around 2000. The year 2000. This is the LHC plot, but this was observed before that at RIC roughly in 2000. And then when the LHC turned on, there was a big surprise when we saw something quite similar in proton-proton collisions, so a much smaller initial state. We also see, you see this is, yeah, so you see a near side ridge here. It's much smaller than the away side ridge, but you still see a double ridge in this plot. And that was a big surprise, because in these systems, it was thought to be the initial state was too small and living too short to produce a thermally equilibrated state. But nevertheless, we saw it, and we also see it in the intermediate P-lead, which is also produced at the LHC. So then the natural question is, of course, what about even more fundamental electron-proton scattering at Hera? Can we see it there too? Like, how far does this go? So this is the Hera Collider in Hamburg. So it took data between 1992 and 2007. And the two principal detectors are H1 and Zeus. And the root S of the collisions is 318 GeV. So there are two regimes of scattering at Hera. The first one, the most popular one to study, is deep inelastic scattering. And that's the case where this exchange photon between the incoming electron and the proton is very virtual. So the Q squared is much larger than lambda QCD squared. And in this case, it probes a very small region of the proton, like as shown here, hitting one quark, for instance. And the dimensions of this region are given here, roughly inversely related to the Q squared. And yeah, so neutral current DIS involves the exchange of a photon or a Z boson. And then the other regime of interest, which was the main interest of this last analysis on Zeus, is this that I performed, is photoproduction. And that's the case where the virtuality of this exchange photon is near zero. So it's nearly a real photon. And then this photon can exchange or can fluctuate into quark and gluon matter. And then that matter then scatters with the proton. So then it's more like it's more hadron-like, this initial collision. And then in this case in particular, you have the possibility of multi-parton interactions, MPI. So in this case, I drew three scatters, three gluon exchanges. So it'd be a case of 3 MPI in this one event. And that's another thing we want to look for. So here's a picture, a rough schematic picture of the Zeus detector. And I have the main cuts listed here on the right. I'll just go over them briefly. So we reject the scattered electron from the analysis in deep inelastic scattering. So in this picture, the proton beam is coming from the right and the electron beam from the left. And then in DIS, you see often a scattered electron in the detector, and that's this dashed red line. So this is used to help identify DIS versus photoproduction, of course. But in analysis, we reject this track because we want to study the produced matter in this interaction. And the rapidity, pseudo rapidity, is negative 1.5 to 2, PT 0.1 to 5. And another important one is that this is all high multiplicity. So and the number of charged particles in this kinematic window is greater than or equal to 20 particles. And that's the same for the DIS sample and the photoproduction sample. So we studied 2 particle correlations, and you'll see later on this CN2, which is just the average value of cosine n delta phi, the phi of particle 1 and the phi of particle 2. And n is the harmonic, which characterizes the shape, the topology of the event. And so I give you a rough schematic on what to expect. So for the first harmonic C12, this 2 here is the number of particles, because you can also do a C14 for 4 particle correlations. But I'm showing 2 particle correlations. So one is the directivity of the event, and the second order, which is very popular in heavy ion collisions to study, is the elliptic asymmetry. So back-to-back back-to-back topologies. And we're going to just focus on these two harmonics. So and before I show more C12 and C22, let's go back to these ridge style plots. So here's our results for those. On the left is photo production. So Q squared less than 1 GeV squared. And on the right is deep inelastic scattering. And you see the near side peak, that's like a jet peak, that's there clearly in both. You see the away side ridge, which is also interpreted as an away side jet, but which is smeared because the axis fluctuates longitudinally event by event. But you don't see a near side ridge in either case here. Now, these plots don't have any systematic uncertainties, as always. So these are just qualitative, but it's clearly not something that just pops out, this double ridge that you see in hadronic collisions at the LHC. Okay, and then now the second part is about MPI. And so that, again, that's cases where there's more than one 2-to-2 scattering per event. So here, this is one from a Pythia publication showing 2 scatters, quark, and gluon. And we assess this MPI using Pythia expectations. And this is an established feature in high multiplicity hadronic collisions, but it has not been observed conclusively in EP scattering. So another interesting possibility that might precede the initial multi-parton interactions is this rescattering phase. So I draw here 3 sources. So these are the 3 MPIs that generate, say, gluons that are emanating from these regions. And this whole region of the MPIs is, it can be very irregular and it changes event by event. And I just drew one particular case here. And then I want to point out here is that you could have a rescattering phase. So that's where the matter or the gluons produced from one MPI scatters with that of another MPI. And this, if you have a lot of that, that is what could produce a thermal system where you might expect this collectivity that you see in heavy ion collisions. Okay, it is a bit far-fetched to assume there's a lot of it in EP, but this, in principle, it could happen. And that's what we want to look for. That's the collectivity. So if there's a lot of rescattering here, then you could expect a collective environment to form. So here's the result in photo production for the multiplicity distribution and in black points, and then compared to various Pythia expectations. Now, the main parameter I'm adjusting is this PT0, and that controls the number of MPI. It just regulates the cross section and also controls the IR divergencies. And then in Pythia, they give an energy dependence to this, and it's based on, I think, quite involved fits. And so the prefactor here is PT0 ref, and that's what I'm changing. And so you should just know that the more MPI there are in the Pythia that I generate is corresponding to lower PT0 ref. So here's 3 choices of PT0 ref, 2, 3, and 4, and the mean number of MPI in each case. So for 2, PT0 ref equals 2, the number of MPI is 8, so that's quite a lot, 8 partonic scatterings, pair partonic scatterings per event. So that's this black line. And then the other end is PT0 ref equals 4, and that's just say 2 interactions, and that's the red line. And then we also switch MPI off, so that's just 1 scattering per event, and that's this gold line. So you can see here that the data definitely doesn't prefer very high MPI, but it also doesn't prefer no MPI, so something in the middle is preferred. There's also color reconnection, which is Pythia's attempt to model the rescattering, and that I show for one case, the PT0 ref equals 3, on and off. Okay, so here's
So you have about 2 minutes left.
Yep, 2 slides.
Good.
So here's the results for C12 here, the first harmonic, and C22, second harmonic on the right, versus the pseudo-rapidity separation of the pair. Okay, and then it's also compared to the Pythia expectations, and you can see very clearly that the very high MPI is also ruled out, and the no MPI case right here is also clearly ruled out in both cases. So the red line is favored here. However, there's some tension now. It's more like the blue line, which is favored here. So Pythia doesn't quite get it all right. But it's clear that the two extreme cases that I show are not favored at all, and that the more and more MPI you add, it seems to dilute the correlations in the model, and that's because you have multiple axes of pair correlations that are all superimposed, so it then kind of washes out any structure in these correlations. So to summarize, I measured two particle azimuthal correlations in Zeus and EP photo production and NCDIS. And we also have many more plots for different projections of the two particle correlations and also 4 particle cumulant correlations. I didn't show those, but they're in the paper and the backup. So there's no clear indication of a double ridge in either gamma P photo production or DIS. So the observations do not reveal a significant collective behavior like that seen in heavy ions or high multiplicity hadronic collisions. And I think that the concept of multi-parton interactions provides a useful tool to help understand the emergence of collective behavior. I would say that it sets the stage for a potential rescattering phase. So I've had this table here to compare EP photo production versus PP high multiplicity, which is basically PP is the smallest system where we have seen these collective effects. And so there's no collectivity seen in EP photo production, but we have seen it in PP. And then the MPI, number of MPI as extracted from Pythia, here compared to our data, we get a number of roughly 3. But the same kind of analysis in LHC PP yields much higher MPI on the order of 20. So that can help understand why we don't necessarily see it with Zeus data, but you do see it with LHC data. So the initial states of both systems might be similar in their spatial extent, because in photo production, the exchange photon splits off into a quark and gluon extended system, which then can scatter with the proton over the entire size of the proton. So just like in PP, so you can see that they can have similar spatial extent, but they are completely different in their number of MPI. Okay, that's all I have to say.
Okay, thanks a lot, Devin, for this interesting analysis of the Zeus data. Does anyone have a question now? Okay, so the study of small system is something that has seen attracted a lot of discussions in the Havian community over the past couple of years. Do you know if there's any theoretical expectation for a system such as EP?
No, I would. So there have not been any serious like hydro. So the theory we use to calculate this collective effects is hydrodynamics.
Okay.
And I have not seen any hydrodynamic calculations for EP. They have extended it to PP, of course, but I don't know of anything in EP. It's not really expected in EP, but then again, 20 years ago, it wasn't expected in PP.
Yeah, sure. Yeah, I guess also with the EIC coming up in the US, that's also something you might want to look at in terms of electron-ion collisions.
Mm-hmm.
I actually have a follow-up question, because naively I think that, a hydro simulation has a few dimensional parameters. The one I was thinking of was the temperature of the medium, which is probably giving you some kind of a reference energy scale. Mm-hmm. And I suspect that even if you take the LHC data for the ridge, you'd see different behaviors depending on the PT of the particles you're looking at. And if they become of the order of the temperature, you might see something. If they become too high, you won't see anything.
Sure.
Sure. Is it something you can look into? For example, maybe not because of the stat you have, maybe not for the full range, but at least in terms of NPI, have you thought about studying how that number, the average number, which is about 3 in your findings, changing when you vary the PT of the selected particles?
So we have another projection that might be given by exactly that. So here's the 2 particle correlation shown versus the mean PT of the pair.
Okay.
And you can do the same thing. You can compare the Pythia to assess this. So this is about as high as we go for this analysis because the mean PT is 2.5, half of this range, or half of that limit. Mm-hmm. And yeah, you can see that it also, there's some tension here because this projection, so this one doesn't work at all. Neither of the Pythia 8 predictions, and they don't change much with the MPI. So this one is not sensitive to MPI. On the right side, though, you do see some sensitivity. However, it's preferring something with much larger MPI, so like the black line or something in between the black and the blue.
Okay.
But you're right. You're right that the higher the PT of the particle, the more likely it is like the jet, and then you would not expect that to be a thermally equilibrated part. You know,
yeah.
10 GeV particle.
You'd expect is lower PT.
Yeah. This should be dominant in low PT.
Okay. Well, thanks for the clear answer.
Mm-hmm.
Anyone else? Oh yes, Olda.
Hello, thanks for interesting talk. I have actually quite naive question because I'm still trying to understand how to map what you are seeing in the EP collisions to the PP. And maybe you can explain to me a bit, because when you collide the electron with the proton, then essentially the multi-parton interaction that you are studying is coming from the photon, that kind of the Hunter content of the photon. And so this is not really directly comparable with what you have in the PP collision, where you have the scattering of the proton. So what are the handles when you are using these 2 different processes to actually compare kind of apple with apples?
So yeah, it is a very different type of scattering. The handles we have are quite basic, and that's like we want to go as high as possible in multiplicity, and you can find something somewhat comparable with LHC studies. Although you're right that there's not really the apples here, because let's go back to that ridge, double ridge. So ours is greater than 20, but this one you can see it's greater than 120 particles, but we just don't have that kind of those kind of events at Hera. So it is hard to make a direct comparison between them. You know, but what I think they can be seen in a similar way, in a similar frame, if you consider the MPI possibility, where I mean, even with the proton. So I have this plot as well. Maybe now that we're talking about it, we can show this. So here's the mean number of MPI, and I have like this evolution of these systems. And so the fundamental collision is DIS, just one photon coupling to a quark. Then MPI possible with photo production, and in PP, I think if you can also see it in a similar frame where there's multiple quarks and gluons in each target and projectile, and then you can have multiple scattering between all of those, and so forth and so on. So I think MPI helps, you know, bridge the divide between this and this. But yeah, they're comparing LHC to us is still a bit of apples and oranges. You're right.
Yeah, thanks. I was more wondering if we can find, you know, selection or kinematic frame where this, you know, hadronic content of the photon would be somehow comparable to what we do at the LHC. Also, maybe well defined there in certain kinematics range, right? So that you probe similar X or things like that, so that then we can actually kind of distinguish the different effects, MPI or FSR and things like that. Yeah. Thanks.
Okay, so I'm afraid we're slightly getting out of the time frame. So thanks a lot for the talk and the interesting discussion.
Yes,
I suggest we move on, and we can always discuss more around coffee later. Well, thanks a lot.
Yes, thank you,
Devin. So we're actually going to move deeper into the West Coast night now, further west. So the next, and back to H1 with Ben Nachman. Ben, you're around?
I am indeed, and it is deep into the night. But
hi, Ben.
Yes.
Yeah.
Yeah. Hey, Gregory.
Okay. Yeah. To some extent, I mean, you can always be still. Yeah. Okay. Deeper into the night depends on time frame.
Okay,
right,
I think
so
I'm sharing.
yeah,
Hopefully.
good. We can see you. I won't. I will let you talk.
Okay, very good. Thank you. Right. So today I'm here to tell you about lepton jet correlations and ML unfolding on behalf of the H1 collaboration. We've heard a bit about Terra, so I won't say too much. And from the last talk, you heard about Zeus, and the talk before that, you heard about H1. So here's just an overview of where H1 sits at Hera, or sat, I guess, at Hera. I won't say too much about what H1 is. Hopefully now you know, given you've been in this session, but just a quick reminder, it's one of the two multi-purpose experiments that was at Hera. I'll be talking about data from Hera Run 2. You can see the specs here. So it's about 100 inverse picobar and 320 GeV center mass energy. The kind of events that I'll be discussing are shown schematically here. This left picture is a cross-section of the H1 detector, and you can see this electron jet event. So we're talking about events that look sort of like the bottom right Feynman-like diagram in the lab frame. So this is the same picture, but now explain a bit more why we're interested in studying this sort of Born level configuration of electron jets. So typically jets in DISEP are studied in the bright frame, and this Born level configuration is actually discarded as their background. However, jet production in the lab frame has found renewed interest. In particular, can be interesting. These balancing electron in the jet can be useful to understand TMD PDFs, among other interesting QCD phenomena, which are why there's renewed interest in this kind of observable. Okay, so we're looking at jets in H1. We use an energy flow algorithm called the HFS to combine information from the tracker shown here in these rectangles, open rectangles, and the calorimeters which are shown in the filled rectangles. And then there's some calibration, and the energy scale is really quite precise, or 1%-ish for jets, and around the same, a little bit better for the scattered lepton. Okay, so one of the key challenges of exploring this lepton jet correlation is that it's defined by multi-dimensional phase space, and we want to be able to probe it holistically. And so I'm going to describe now a machine learning based technique for exploring this phase space. Okay, so there's going to be now a small aside into how to do multidimensional and unbinned unfolding. We're using this tool called Omnifold. So the idea here, in general, for unfolding is that we want to use as input detector level data, top left, to extract the particle level truth, top right. And we're able to do that by using simulations, which are on the bottom, and we have a match between the particle level and the detector level. Okay, so briefly how this procedure works is you want to do what this arrow shows here, go from the top left to the top right. We do that by first taking our detector level simulation, reweighting it to data, and then we have a set of weights, and then we use the fact that in the simulation we have a match between particle level and detector level, so the particle level events also have a weight, which is inherited from detector level. And that's not the end. We can't just stop there, because the stochastic nature of the mapping of the detector means that a single particle level phase space point can be mapped to multiple detector level phase space points. So we need a regularization step, which makes the particle level weights a proper function of the particle level phase space. And we do that by doing a second reweighting step to reweight the unweighted particle level phase space to the one with the weights drawn from the detector level, and this sort of averages over the weight so that at a single phase space point you have only a single weight. And in principle, we could stop there. So now we have a weighted particle level simulation that is supposed to look like the target. But we can repeat the procedure now. OmniFold is iterative, so we can once again use the mapping between, or the connection between particle level and detector level, use those weights to get a new detector level simulation and repeat the whole procedure multiple times. So that gives you a second iteration. You can repeat it n times, like other iterative unfolding techniques. Okay, so that's how OmniFold works, and the result is that we have a particle level simulation with a bunch of weights. We can then use that to construct histograms or other statistics. Okay, so this procedure is inherently unbinned. I didn't prove it to you, but it achieves the maximum likelihood estimator like other unfolding approaches. In principle, it can accommodate a large phase space, and it can improve the resolution from additional features. I haven't told you how we do the reweighting, and that's where the machine learning will come in. I'll describe that in just a second. In this measurement, we're simultaneously unfolding the lepton and jet kinematics, and we're going to report bin spectra for the jet PT, the delta phi between the jet and the electron, the QT, which is the momentum imbalance, and the jet eta. Okay, so the reweighting itself is done with neural networks. That's the magic of this approach, because they're naturally unbinned and readily process high-dimensional data. And we use a fact that you can take a classifier trained to distinguish between two samples as a likelihood ratio approximator. So there's this trick that's shown here on the slide. You train a classifier to distinguish two samples. The ratio of the classifier output will allow you to basically estimate the likelihood ratio in an unbinned way. And we do that, this is illustrated here, where you can see Q squared, where we have two simulations called Django and RapGap. And we train a classifier to distinguish Django from RapGap, and we interpret the output of the classifier as a weighting function, and we can morph the purple into the black, and the black matches the green. Here it's shown bin, but this is actually unbinned and only bin for illustration. So this is only in one dimension, but actually it's straightforward to do this in a number of dimensions. So we do this in 8 dimensions. The actual unfolding that we perform is 8-dimensional. We have the 3 momenta of the lepton, the 3 momenta of the jet, and then we add QT over Q squared, as well as delta phi, which is redundant, but from this we can readily calculate the 4 observables that we care about. And here, once again, we're rewriting the purple. We're training a classifier to distinguish purple from the green. We interpret the classifier output as a weighting function. We morph the purple to black, which matches the green, basically everywhere. Okay, that's one step of OmniFold. And then we wanted to be able to then iterate. So that was just detector level reweighting, but then we have to do this iterative procedure. And when it's all said and done, we can look at the particle level results and check in the closure test if we unfold here, for instance, one of the simulations with the other. Here, the idea is that we're unfolding Django with RapGap, and we want the unfolded Django to look like the Django truth, not like the RapGap truth, which is the prior. And everywhere you can see that the black matches the orange, which is exactly what we want. And so this method closes well across this 8-dimensional phase space. Okay, so we recently put out a paper where we did this measurement of electron jet correlations in the lab frame. And I'll briefly summarize the results here now. So here are some plots that show the uncertainties. Let me just draw your attention to the top left one, which is the jet PT. And so you can see we're able to probe jet PT up to about 80 GeV before we start running our statistics. So there, the statistical uncertainty is something like 5%. And otherwise, the uncertainties are really quite small, so 1%-ish. And this requires, of course, an excellent understanding of the detector, as well as a robust unfolding procedure that allows us to beat down the fluctuations from the inherent nature of the training. And you can see, okay, there's eta, delta phi, and then also QT over Q in the bottom left, where we're able to probe QT down to something like a few percent. Okay, here are the results. Left is QT over Q, and the right is delta phi. These two observables are very related. So low QT corresponds to low delta phi. So delta phi here is defined as this pi minus what you might think delta phi should be. So low delta phi is actually very back-to-back, which is the low QT region as well. And we have an excellent agreement with a lot of different calculations. So you can see here Monte Carlo generators the usual suspects, Pithy and Herwig, from that are been tuned heavily in PP collisions. And then there's Django and RapGap, the favorites from Hera, and then Cascade, which is a TMD-based Monte Carlo generator using the parton branching method. But also interestingly, you can see comparisons with analytic calculation. So there's a fixed order perturbative QCD as well as a TMD calculation. And what's really exciting about these is so that the fixed order calculation is expected to do well at high QT, and the TMD calculation is expected to do well at low QT. And there's this intermediate regime of sort of like 0.5 or so, where the two calculations are expected to have overlapping agreement. They seem to agree well with each other and with the data. And the data can then be used to help understand sort of the connection between these two frameworks for a complete picture of these events. Okay, we also have PT and ADA, so PT on the left, ADA on the right, once again compared with fixed order calculations. Interestingly, although not shown here, is that for ADA, it's actually really important that we have the next to next deleting order because the corrections from next deleting order are not small. And actually, in fact, the n cubed LO corrections are also not that small. But over a wide range of many decades, for instance, in PT, you can see this excellent agreement with the perturbative QCD calculation, and there's some disagreement with some of the Monte Carlo generators, in particular Pithy and Herwig, which is interesting to explore. In Herwig, for instance, it's not tuned at all. Pithy and Herwig are not tuned to these data, but are still able to describe qualitatively over a large range and quantitatively over a slightly more limited range. Okay, so that's the results. One thing I will mention is that even though we present these four histograms, the unfolding is done simultaneously, actually in 8 dimensions, but shown here in 4. And sort of the correlations between all the observables comes for free because it's done simultaneously. And here's a plot that shows the correlation between the 4 observables. And as you might expect, PT and ADA are pretty uncorrelated. But then as I advertised, QT and delta phi are quite correlated. You can see from these large off-diagonal terms in the upper part of this correlation matrix. Okay, so looking forward, we presented here this machine learning based unfolding, but it's at the end presented as 4 independent bit histograms. And so we'd, of course, eventually like to use this technology to present results unbinned. And publishing unbinned measurements is a bit tricky. And we've started a conversation about this in this recent paper, as we expect, or we hope, that there'll be more results of this kind. So unbinned and simultaneous in many dimensions in the future. And we're looking to see how this can be done in sort of a uniform way across different experiments. And this was a recent effort to try to identify ways of doing this coherently. Okay, that basically brings me to the end. Today I've presented the first machine learning based unfolding with collider data. This is the start of an exciting program to advance our study of QCD into higher dimensions. Starting here with H1 data, but looking forward to related DIS data, as well as data from EP, EA, and PP. This particular measurement has important constraining power for TMD PDFs. As I mentioned, we're able to probe this interesting regime where we're sensitive both to sort of fixed order perturbative QCD at higher Q, and then higher QT, and then TMD PDF effects at lower QT, and they're sort of matching in the intermediate regime. And hopefully this provides an important input also to planning and design for the EIC. That's it. Thanks.
Thanks a lot, Ben, for presenting this attempt at doing unbinned distribution, or the first measurement of unbinned unfolding. I'm sure there has to be some questions. So who's going to ask the first one? I'm really getting used to this. But yeah, I actually have 2 questions. The first one is probably one you would easily, well, hopefully you'd expect both. I guess you've compared your unbinned unfolding with more standard approaches, and what does the comparison give?
Yeah, for this particular study, we did not compare. So this, of course, when this method was proposed, we extensively compared to other methods. In particular, you can think of this unfold approach as sort of the unbinned machine learning based version of a standard well-used method called iterative Bayesian unfolding, or Lucy Richardson deconvolution. It's more, if you do that method, if you do unfold binned, it's basically the same thing as IBU. And we know that, I mean, not for this analysis, but for when the method was first proposed, it was extensively studied and compared, and it does indeed sort of match your expectation in that case.
Okay, yeah. And you do get unfolding uncertainties the same way.
The unfolding uncertainties, right? So there's, let me go back to my uncertainty plot. So most of the uncertainties you get the usual way, as you vary some aspect of the simulation, and you see its effect on the unfolding. You basically repeat the unfolding, and you see the result.
With the same thing as your closure tests. Yeah,
exactly. In the closure test, you unfold one with the other, and so it's sort of the same idea. As there's nothing special about the what's done here. It's exactly the same as the usual way. Everything is once everything is projected back into bins, it's basically just like normal bin unfolding. It's just the intermediate. The only difference is that here, if I want to change the binning, it's trivial. I mean, it takes me 5 minutes instead of 5 months. So yeah.
Yeah, the other thing I wanted to ask is still about this unfolding, but maybe in a different direction. How far can you push it? In the sense that multiplicity is not that high in a DIS environment. Can you really push it to unfolding the full event?
Yeah, so I kind of view this as one step in a larger program, clearly. So the first thing we have to do, the next step after this is sort of a baby step, if you like, in the sense that we at the end of the day are presenting only bin histogram, these 4 dimensions. But the next step is to probe more of this 8-dimensional space that I mentioned we unfolded, and stay tuned for that. We'll have something hopefully to say about that in the not too distant future. But then, yeah, indeed, we want to push it more and more. And I also can say with confidence that we're not the only people in the world trying to explore this kind of high dimensional examples. And some of my colleagues who might know more about that are in the room. But indeed, I think it's an exciting time, and I would say stay tuned.
Yeah, I guess in terms of baby steps, LEP would be a step in between this and more complicated events like DIS.
Indeed. I mean, I guess I can use this platform to briefly just say that, of course, like, as you can tell by my age, I guess, that I was not around at the time of the collection of these data, but it's been a fantastic experience working within the H1 collaboration who welcomed me, and I've learned a great deal, and the data are in a fantastic shape. All the software and simulation tools are really modernized, and that allows for these kind of analyses to happen, which is not something I can say about, say, some of the other data sets that are taken around the same time. Yeah.
Okay, well, thanks a lot, Ben, for this very interesting talk. And I see no other hands raised. So we'll move to the last talk of the series with Hangne. Again, I apologize if I didn't pronounce this properly. And we again switch gear a little bit and go to proton-lead and lead-lead collisions for LHCb. So,
hello, can you hear me?
Perfectly well.
Good.
I can even see your screen.
My screen. Let me start slideshow.
Good. So, yeah, I'll tell you when you're close to the end.
All right, it's full screen. Can you still see it, right? All right, so today I will talk about the PTAD and lead clearance in former region. Basically, we're talking about RCB results, but the title is too big, right? So basically, in fact, I will only cover 3 analyses in today's talk. These are there are 2 photon-induced and production of Jepside Z2S, and also a Jepside production. Also a charge, the prompt charge hadron, charge particle production in PDAD, and also compare with PB clearance. These are analyses that we recently submitted. All right. Let me first very briefly introduce the RCB detector. Probably you have already known this is very dedicated forward detector that fully instrumented in the forward region with kinematic coverage from 2 to 5, and this is is a good complementary to Atlas MS, and because its design is for forward, so the magnetic field is up and down. Yeah, it's not solenoid. So it's up and down. So it's very much designed for high precision measurement for low PT. Yeah, and it has very excellent particle ID and very precise vertex. and tracking reconstruction. All right, so the RCP detector was designed, it's mostly designed for CPU violation studies, physics, but it's also good for the heavy ion studies. Here we have the, I'm trying to show you, we have the collider modes of the PDAT clearance and LEDAT clearance, and also we have the big target modes, which basically we inject gases in the interaction points when the collider beam colliding with each other is also tied with the gases. So, but today I will not talk about quick target clearance, but the collider modes clearance, and I will do 3 analysis here using 2015, 2018 LEDAT clearance, and also the PDAT clearance taken in 2016. And on the right side, you can see the kinematic coverage of the is the center mass energy as function of the rapidity in the rest frame. All right, so the first analysis, we call it PC. So basically, so this is not really two that is not really connected with each other. So they just bypass each other without clearing. But in fact, there's the photon-induced clearance. You have the photons around the nucleus. So here we have the photon-induced interactions can enhance by this strong magnetic field of the nucleus. And on the right bottom plots figures, you can see that, for example, in case of the so we have this kind of Jepside production. We call it coherent Jepside production, which is a photon interact with the nucleus as total coherently. So basically, you're exchanging 2 gluons. And the other one we call it incoherent. Basically, we exchange the photon exchange a pair of gluons with one of the nuclei. Okay, and in the later case, it's just break up. So this kind of analysis can be very helpful to study the gluon probability density functions in the nucleus. All right. So this analysis is done in this way. So first, it's just measure the cross section of the coherent production. So as you can see, we just define the cross section in the common way, and the event selection. Basically, if you have the photon induced production, basically you only have a Jepside. The 2 nucleus just do not break up, right? So in a detector, you only have 2 long tracks, very clean long tracks in the very forward region. So we basically require a very empty detector, and here is our class to select the Jepside, and we require the PT of the Jepside to be very small. And we also employ the so-called Herschel detector, which is, if there are some breakups in the very, very forward region, so it detects some signal, so we just remove this event. And the signal extraction is done in this way in 2 steps. First, as you can see in the right top plots, so this is the invariant mass of the diamond system. So you have the Jepside, you have the 2s, right? And you first use the invariant mass to fit to have the Jepside signal. And then you're going to extract how much is the coherent part. So in this way, we use it. In this step, we use the log PT square. We just zoom in this PT region. So we select a very small PT part, which is the coherent production. Is this PT range is basically inversely proportional to the radius of the lead nucleus. All right, so here is the results. This shows that plot shows the differential cross section as function of the rapidity and comparing with different theoretical calculations, including the perpendicularity calculations and also the color dipole modes. Okay, and basically it's our 2015 data set results agrees well with most of these calculations, but we can also see those theoretical calculations are divergent, can be very different. And on the right side is trying to compare our results with the Alice forward region results. As you can see on the right plots, this is the Alice results showing both the central region which is between around 0 in rapidity and the forward region. And there is little differences, about 1.3 sigma differences, but it's actually we would say it's compatible with each other, considering these uncertainties. But the negotiation, the discussion is still ongoing between these two collaborations. All right. At the same time, the 2018 dataset results is about to be to get out. Here we have about 20 times higher statistics. You can see our approved plots showing these higher statistics. You can see a much smooth fit of the trypsin sentimentals, very clear signal. All right. Now let's move to the second analysis. So this is so-called a peripheral photon produced photon production of trimonium. So peripheral we define to be the clearance happens. The impact parameter, the distance between these two lead are smaller than the 2 times of the nuclear radius, but greater than 1 times of nuclear radius. Or in terms of centrality, we are saying that the centrality is greater than 50%. Okay, so they're really collided. So in this kind of clearance, we can see 2 parts of the trypsin production. Yeah, it's very interesting. You can have the traditional trypsin hydronic production of trypsin. You can also see the photon-induced production. Yeah, so you can see the 2 parts. So this is motivated by the excess and by the Alice experiment. Okay, now this is the first 2018 LELED dataset results, and the selection can be very similar to the UPC analysis, which basically requiring very small PT, and it's also done in 2 steps. So in the first step, you fit the environment mass of the trypsin, you get it, all trypsin, and in the second step, you use log PT square to separate this small bump. The bump has small PT square, which is a photon-induced one, and the bump has a large PT square, which is the hadronic one, right? So you can separate the 2 parts and use a fit to extract the photon-induced one. Okay, all right. So the measurements results can be shown here. So basically we can see consistent measurements of trypsin photon production in the leaded hadronic clearance. And this is the most precise PT measurements to date, and also it's the first time of the PT spectrum measurements. And also the results are compared, because at that time when we submit this paper, so we still don't have the integrated luminosity measured by the collaboration. So what we show in the paper is the use. Basically, the use is a ratio between the number of trypsin and the number of millibaseconds, which just takes the number of millibaseconds as the here. All right, so it's compared with the 2 theory models with 2 assumptions. One is no effect of overlapping between the nucleus, and the other is overlap has an effect, right? So here are the references and the results showing left bottom plots. This is the yields as function of the rapidity of trypsin, and in the middle is the yields as function of the PT of the trypsin, and the right side is just showing the yields as number of particles. Okay, basically you can see a pretty it's not so agree with each other, but considering the uncertainties, it shows a good agreement with the theoretical predictions. All right, now let's move to the third analysis. So this is the prompt charged particle production in PNET clearance, and also provide the it's also give the nuclear modifications, which is defined as the ratio between the PNET and the LED cross sections. So by the so-called prompt charged particle, we basically measured the reconstructed tracks, right? Reconstructed tracks, just define the reconstructed tracks following some definitions. For example, the leptons directed from clearance from the decay of with lifetime smaller than 30 picoseconds and PT blah blah, and in such a range. Okay, and the data set. So data set we use the 5T PNET and also the PP glaring data set, and this measurement is measured in the common eta coverage. So because the p-net has a boost in the direction. Okay, so motivation of this analysis. So yeah, so basically we are using this to constrain the nuclear PDS, right? To study the cold nuclear matter effect, and RCB have really the coverage of European X and Q square down to very small European X, and also for the very big European X. So this can be a good complementary part compared to other experiments. And for sure, this analysis is reconstructed, tracked, and also corrected from the background and also the efficiencies, etc. All right, so let's move directly to the results.
So Hagne, just about 2 minutes left.
Okay, yeah, it's about to finish. Okay, so the results. The left side shows a differential cross section for the S function of eta and the PT, as you can see. So the precision is pretty good, and the utilization part is on the right side. So this is the nuclear multiplication factors. So basically, it's the cross section of the p-net over pp. So on the top part, it shows the forward one. So basically, you can see you can see our results compared with theoretical predictions, and you can see clear suppression for the low PT part. And yeah, the agreement with the theoretical prediction is pretty good for the forward part, and but for the backward part, so you can see very big differences, right? And you can even see some enhancement for a higher PT part. Okay, so this can provide very strong constraint to the nuclear PDS. And also compares ALICE and CMS results, and the left side shows the shows the different colors, show different eta coverages, and you can see the trends, right? So when the rapidity from positive moves back to negative, so the enhancement for the high PT part is you can clearly see this trend. And also on the right side, so this is some new observables. So this is just trying to mimic the Q square and European X, and you can also see this trend very clearly showing here. All right, come to conclusion. So basically, we are doing 3 analyses: harmonic production of lead ultrapure clearance. So this is a refined analysis with good agreement with theory, and the 2018 dataset results are on the way. And also the Japanese study in the peripheral clearance of lead. So this is first lead results of the 2018 dataset, and also the first determination of nuclear modification factors using the charged tracks or prompt charged particles at RCB. So this clearly shows very strong constraint to nuclear PDS, and more new results are coming. Thank you.
Okay, thanks a lot, Hagne, for this very nice overview. Questions, please. No. So I wanted to ask something about the charmonium production. So if I understood correctly, your results are a little bit smaller than what Alice is seeing. That's for the. I suspect that's for the same. Well, is it an apple-to-apple comparison? Was the first thing I wanted to say. Is it the same? Same
Not really. Yeah. So it's basically the same kinematic, but Alice is using 2018 data. We are using here. We are the 2015 data set.
Okay.
But it's basically should be agreed. And also, if we analyze the Alice data and compare with these theoretical predictions, and we can see that their forward and backward are not in the, at least not under the same theoretical prediction, right?
Okay. Yeah, I guess the ultimate goal of this would be to constrain the well, to be able to disentangle between these different theory models, right?
Mm-hmm. Right.
So is that something for which you'd expect something better with your ongoing analysis of the 2018 data?
Right. Our 2000 sorry. Could you please repeat your question? 2018 data.
Yeah, you mentioned that you were in the process of analyzing the 2018 data. Is it something for which you'd expect essentially smaller uncertainties and so a better discrimination between the theory models?
Right. We are expecting smaller uncertainties with the 2018 data set.
Okay. Yeah, maybe another question. I'm not sure if that's relevant or not, but would you gain anything by studying epsilon instead of JSI?
Sorry, could you please, I'm not sure I follow your question.
So you studied JSI production. Could you study also epsilon production? And would that be any helpful?
Okay, so Wupsilon, we are looking at the data set. Even the 2018 data set, we don't see much of the events. Yeah, we see some 10 events, and if we are talking about the coherent one, so basically we have, we also have some theories to do the calculation for us. It's consistent with 1, 2 events, 3, something like that. Not much.
Okay. Thanks. Yeah, maybe a last small point was about the measurement about charged particles, the RPA ratio. You mentioned this could constrain nuclear PDF extractions. Have you tested different nuclear PDF sets? I think there are more recent PDF sets than EPPS 16. Do you know if there's any improvement with more recent nuclear PDF sets?
We don't know. For this analysis, we didn't try those. For example, NPDF 3. There's nuclear NPDF, right? And also some.
Yeah, I was more referring. Yeah, it's the RPA ratio. So I guess the nuclear PDF is the thing you want to look at. I thought EPPS had a recent analysis, 2018 or maybe even last year or something. I can't remember the exact details. I think there's a more recent one.
All right. Yeah, so yeah, these results is getting out, and I believe those people, those collaborations, the nuclear PDF collaborations will look into it.
Oh yeah, that definitely looks interesting.
Yeah, and so the thing is here is really the small the dedicated this special kinematic region. Previously, we probably don't. The series don't have the data to constrain. So this probably it's just extension from other BRX region to this region, to small X.
Yeah, I agree. Okay, well, thanks a lot for the clarifications. Okay, Alda.
Yeah, I have a question on this slide as well. So for this EPPS 16 predictions, what is the systematic uncertainty in these predictions? And then the second question is, yeah, in this negative eta region, the Parton QCD calculation is completely off. Do you have some understanding of why it's so?
First question. So this uncertainty includes the nuclear modification factor uncertainties, and I'm not sure if it's including the PDF uncertainties or not. This I'm not sure. Okay. And could you please repeat your second question? I didn't catch it very well.
I was asking about this perturbative QCD calculation that is compared to this negative eta separation ratio. If you can just give us some feeling why it's so off.
Oh, okay. So this is basically not the basic QCD part can be solved. It's just showing here. Think about so the production of hadronic the charged particle production. So you have the factorization, right? So the non-perturbative part is stored in the nuclear PDF. Yeah, and then the hard scatter is calculated with the PQCD. And if you are not considering the non-perturbative part, right, from nuclear PDF, you cannot get it correct.
Yeah, but I mean the discrepancy is also at a high PT. So of course at a low PT, then you have some other effects. You probably have to do some resummation. But even at high PT, this is going of the data.
Right. So the enhancements, right? So I don't know. Basically, I don't know. I don't know.
Okay, thanks.
It's interesting to have the so thank you. The low PT suppression is known already in the very studied Iraqi aspiration, right? Like the power. I don't know. Good question. I really don't know. It's subject to some further study, definitely.
Sure, thanks.
Yeah, I guess nuclear PDFs could probably be just slightly off there. I guess it's maybe a bit premature to draw any hard conclusion. Anyway, so I think we're slowly reaching. Well, we're actually slightly over time. So I suggest, is there anyone who has any burning question to or comment? So if not, I would really like to thank again all the speakers of this session that think that well extremely well, and then I want to wish you I don't know, depending on where you are, good appetite for a lunch, breakfast, or dinner, or a good night if you're somewhere in the middle of the night. And so I guess according to the program, there's now a 2 hours break, and then things are going to start again at 2 p.m. UK time. I'll let you do the shift wherever time zone you are. And thanks to all of you for both the talks and attending the talks and the questions. And I guess I'll see you around later in the week.